Hi everyone, I'm Justin, and I'm here with Dean to talk CAN networking basics. While I'm going to touch on a couple of things that are specific to FIRST, most of the following information actually applies to any CAN network. So let's start with the basics. First, the FRC CAN networks are configured to operate at 1 megabits per second. This is in contrast to many industrial and automotive links that run either 250 kilobits per second or 500 kilobits per second. Basically, we benefit from higher data throughput by running a higher bus speed because FRC robots should never get anywhere near the 40-meter maximum bus length allowed by the CAN standard. With that said, at 1 megabit per second, we get about 7,800 standard 8-byte messages with extended identifiers every second. This sounds like a lot, and it is, but keep in mind that many devices send or expect certain messaging every 10 to 100 milliseconds. This gets you down to about 80 messages per robot control loop at the extreme. On a robot with 10 or more smart motors, IMUs, and other sensors, we can actually start getting close to what's theoretically possible on our CAN network. In short, don't request more data from devices than you actually intend to use, especially if you found a way to install 15 motors on your robot. Electrically, the FRC CAN network is like any other. It's a 2-wire bus designed to allow dozens of devices to talk to each other with a single network backbone that connects devices, also known as nodes, on the network. CAN is a differential bus, meaning the voltage difference between the high and low lines is what differentiates between zeros and ones. The network lets only one device speak at a time with a transceiver and message priority scheme that's beyond the scope of this video, but know that to function properly, the bus needs a pair of 120 ohm resistors, one installed at each end of the bus. These act as a terminating impedance to bring the bus back to the recessive state and to absorb any electrical reflections in the network. You may not have realized it, but the RoboRio and PDP both have built-in terminating resistors to meet this requirement, with the resistor in the PDP being jumper disableable. The Rio's resistor can't be disabled as it is meant to act as one end of the CAN bus. That said, if you have more advanced CAN networking needs, such as a motor, controller, or IMU mounted at the end of a long arm, you may need to disable the PDP terminating resistor and install your own at the most extreme end of your network to meet network design best practices. Whatever your layout, never have more than 2 terminators in your network. So now that we've covered the basics, let's move on to network topologies. This topic tends to hold a sort of mythical status, but it's actually fairly straightforward to implement a reliable CAN network on your robot. As we've already discussed, it's basically a terminating resistor, followed by a bunch of CAN-enabled devices, some wiring, and at the other end, another terminating resistor. How you get there matters, however, so let's start with network topology that most people are familiar with, whether you know it or not, the daisy chain network. This network topology is implemented by having 2 CAN connections per CAN device and simply daisy chaining the network from device to device. In fact, most FRC CAN devices are like this, whether you're talking about the Rio, PDP, VRM, or pneumatics module with 2 2-pin CAN connectors, or devices that come with 2 sets of CAN wires like the SparkMax or Talons. This wiring and connector scheme is good for electrical noise by creating a long network with close to zero-length CAN nodes, unless you put both the Rio and PDP on the same end of the network or unwittingly disable one or both terminating resistor. Even bus termination is trivial. The downsides of the daisy chain network topology are the relatively messy CAN wiring routing that you often end up with, and the dreaded single point of failure that's capable of taking down much or possibly all of your CAN network. In this example, a break or loose connection to a single motor controller results in losing everything from that device onward, assuming that the bus is happy enough running with a single termination back at the Rio. This brings us to our other topology option, the star network. Now, you may be thinking something like this, but that's not what I'm talking about. Knowing what we've already discussed, we know that a network like this would be difficult to terminate properly and could cause reliability issues. What we're really talking about is a short drop architecture, allowed by the CAN standard, built off of a typical daisy chain network. For an example of this, we look to Dean. As you can see, Dean has a couple of the usual FRC components mounted in the usual FRC places. The RoboRio has the terminating resistor enabled and is connected directly to the pneumatics module. This is where the usual ends, however, as a daisy chain output from the pneumatics module plugs into a 4-drop star distribution board that connects the left side Venom smart motors. The end connection of this star board is connected to an identical 4-drop distribution board that connects the right side bank of Venoms, as well as a CAN term terminating resistor to complete the network. Dean's CAN bus has a total length of around 4 feet and a total of 12 network connection points. Analyzing this layout, we see that 6 of these connections are capable of taking out at least half of the network, and most of these are the connections closest to the Rio. A mistake or break on any of the other 6 network connections results in only a single motor being disconnected, and Dean still drives through your match. On the other hand, if we had laid out this network as a traditional daisy chain network, the total network length would have been longer than 12 feet, assuming you didn't trim down the leads of the most common motor controllers. Additionally, the connection count goes from 12 to around 16, with 9 of these at risk of taking out at least half of the network. In fact, there's only one failure point that results in only one motor being lost, meaning you're almost an order of magnitude more likely to encounter a match-ending CAN network failure with the traditional daisy chain topology than with a short drop architecture. Thanks for joining me, and I hope this information has been useful to you. With everything that we covered, I'm sure that there's something that isn't clear, maybe something that we missed, so please feel free to contact me at technicalsupport@playingwithfusion.com with any questions you might have. If this has been useful to you, please hit subscribe below to keep up with Dean and me as we demonstrate products, controls concepts, and more. Thanks for watching.